foiled. Let's see. Put it there. Did I record? Yeah, I did start recording. Okay. I don't want to look at a picture of myself, so I'm just going to put it onto my website or something. Okay, so the standard derivative, right, is so the derivative of f with respect to x is the limit as h goes to 0 of f of x plus h minus f of x all over h, right? And there's a few different definitions that kind of look like that, but that end up being roughly equivalent. This is your sort of additive derivative, which is really all we talk about in general. Why do you think we call it an additive derivative?
Is it because it's x plus h?
Yep. Can you think of an alternative?
X minus h? Would you have to switch them around?
Yeah.
F of x minus f of x.
Kind of the same thing, right?
Yeah. We talked a little bit about that in
You did.
computational, I think.
Yeah, directional sort of.
Yeah.
Yeah.
Where the h is on the right or h is on the left.
Or like the
center.
middle. Yeah. Yeah. Can you think of something that would be mind-blowing?
My mind is currently intact, so probably not.
Okay.
Is it like a multiplicative derivative?
Yep.
Oh.
Okay. It's called the quantum derivative. There's a good reason why it's called the quantum derivative.
That
But
sounds like it's found uses in quantum physics.
yep. X. Is that right? Minus x. There you go.
Yeah.
So some possible directions you could go with this are, like, I'd suggest you start by playing around with it a little bit and just see, like, what's the quantum derivative of, I don't know, x? What's the quantum derivative of x squared? Maybe see if you can come up with a power rule, right? So, like, what's the, I should really write this as like this. Like, what's the quantum derivative of x to the n? Is there a rule for that? Maybe you can come up with what the quantum derivative of f of x times g of x is. Maybe you can come up with what the quantum derivative of f of g of x is. Maybe figure out what the quantum derivative of, like, the exponential is. It's a round equal sign. Or the quantum derivative of sine.
Yeah, that last one's not happening.
No,
No, I can't do trig.
I pretty much
can't
agree.
do trig to save my life.
Well, you don't have to do trig to do sine, right?
Yeah, I
Let's
guess.
throw it into a power series. Or Taylor series.
I guess.
Yeah. That's how I would do this derivative. Hey, how's it going?
Hello.
So, I was just saying, you guys had a shit show of a last class.
Oh, yeah, the table.
That table's broken? Is this table broken? No, it's not.
We did.
You did. I think, because you covered derivatives and integrals and did a quiz all at the same time.
Yeah, I got a bunch of questions.
Yeah, we can chat about it. The goal for today is that I was trying to think of the best thing that I could do for you guys. And I think it's a step in mathematical maturity. So we're doing something basically different. We're doing quantum derivatives, although I'm happy to answer questions about anything. But I put up quantum derivatives, so it's this new definition of a derivative.
Quantum?
Yeah, has to do with, it's used in quantum physics. Because this derivative doesn't make any sense in quantum physics. This derivative does. So basically my goal was just saying, like, here's the thing. Figure out how the math works with it. Is there, you know, what's the product rule? What's the quotient rule? What's the power rule? What's the chain?
Is that what curl is supposed to be say limit?
Yeah. Yeah. I'm a good bad writer. That's how I'll put it. But yeah, if you have questions about like actual stuff, we'll do that too. And if you get any answers about any of these.
That's cute. Is that just a limit?
Yeah, it's just instead of H, use Q. Yeah. So in this case, you're thinking about like, so like, as x approaches, or as h approaches 0, the top approaches f of x minus f of x over, I guess this should this be plus? Let me double check it. Because I might have just written up the formula wrong. Quantum
I don't know if I'm doing something wrong, but I'm finding that the quantum derivative of
Oh,
f of x equals x is infinity, which I feel like is not.
does that change anything for you?
Yeah, probably.
Okay. I just copied it wrong.
Yeah, that is one. Is that
That's my
one?
fault.
Yeah, then it's one, right?
Yeah.
So we get rid of that. Q is fine. Yeah, that's okay.
Yeah, so like with the normal derivative, you have f of x minus f of x over h approaches 0, so it ends up just being 0 over 0 if you were to just plug it in. The same kind of idea happens with the quantum limit, right? So as q approaches 1, you get f of 1 times x, just x minus f of x over q approaches 1, so x minus x is 0 over 0. So it's the same idea. It's just you're getting closer and closer and closer to that 0 over 0 to figure out what the tangent actually is. The reason it's quantum is because the jumps you make in this are discrete. They're quantized. So they work with quantum physics and quantum groups. Yeah. So yes, it should work out that the quantum derivative of x should just be 1. But it's not true that the quantum derivative is the same as the normal derivative.
No, I didn't.
It just
That's
works
super.
out nice this time.
I just wanted to at least like calculate it for one thing.
Yeah,
Or get an
it's
idea for
important.
how it plays differently.
That's a good first step.
So every quantum derivative is one?
Nope. No, shouldn't be. Because for example, if you did x squared, you would get q squared x squared minus x squared over qx minus x. The top becomes a difference of squares. That bottom is the same. This cancels with this. Is it just 2x? As q. Oh, I guess it's just x times 1 plus q is the quantum derivative of and as q approaches 1, you get 2x. So you should find that as q approaches 1, you get the standard derivative. But it lets you leave q as q. So it's not always 1, but could be 1.
So if you had a 3x squared, would it be x3 plus q? That's just a guess, right?
Good question. I don't know. Let's see. 3x squared. So f of 3x. So we should get 3q squared x squared minus 3x squared over qx minus x. So this is root 3qx plus x times root 3qx minus x over qx minus x. This cancels with this. This can multiply in with that. You get 3qx plus x, which is 3 times 1 plus q times x.
So 3x plus 3q. There we go.
Yep. 3x plus 3qx. So it looks like, at least on the surface, you can pull out factors, multiples. And maybe you can prove that in general, right? Since it feels like it. If like, so assume something like f of x equals 3 times, or instead of 3, let's do something general, k times g of x, and see if the derivative of, like, see how the derivatives work, right? Can you just, is it true that the derivative of g of x is equal to, or sorry, derivative of f of x is k times the derivative, the quantum derivative of g of x? Can you just pull the k out?
We don't take quantum math in our program, do we?
No.
Okay, that's promising. I don't know what this q is, I'm just kind of thinking it's a number.
Yep, that's exactly what it is. Just like h in normal derivatives, it's the variable. Another variable. How's it going?
I'm hypothesizing what the power rule is and seeing if I can prove it.
What do you think it is?
The same as normal derivatives. Just because, maybe I should have checked more cases first, but it looked like for x to the 1 x squared it was the same.
Yeah, I wouldn't think it's the same for x cubed.
No? Maybe I should have done more cases on it.
Let's see. You know the difference of cubes?
No. Wait. You got a minus b,
Yeah.
and then a squared plus ab plus b squared.
That's right.
Let's fucking go.
Should the bottom be cubed as well?
No. Because remember, if you just apply the function on the top, right? So if you look,
Oh, because f of x and then x on the bottom, okay.
yeah, it's just normal variables on the bottom. So here we get, so a is qx, so we get q squared x squared plus qx times x, so qx squared plus x squared. It's like over qx minus x. You get that?
So it is 3x squared.
Is it?
The qx minus x cancels, right? And then you get x squared plus x squared plus x squared when q is approaching 1.
where's my lapse in understanding here? Because the answer is no, it's not.
It's not fixed, right?
But it is when q approaches 1. But let's see. Q derivative. The q derivative is not the limit. You can take the limit and you'll get the regular derivative.
Oh, but it's not the limit.
It's not the limit.
Okay.
It lets you be flexible in what you pick q as. So
Okay.
here, the quantum derivative should be 1 plus q squared times x squared.
Okay.
You'll notice over here, it was 1 plus q times x.
Okay, so yeah, it matters what you do with the Q.
It does.
So doesn't that change everything?
You don't get rid of the q, you just leave it. You can pick any value for q, it's a second variable,
So,
in a way.
Okay, so just factor out x.
So I guess I should get rid of this to be nice.
Well, new hypothesis. Let's see if this one's right.
What's your new hypothesis?
Well, the one hiccup is that, no, so this isn't for 1, this is just Q.
Yep.
Yeah, this is Q on 1.
Is it?
Is it? For f of x equals x.
I don't think
If we're not taking the limit of q of, it's qx minus x over qx minus x, that is just 1.
Yep.
Is it
So that's,
x to the n minus 1 times q to the n minus 1, q to the n minus 2, dot dot dot, q to the n
Yep.
minus n?
Yeah.
it works because it's x to the
Yep.
0.
So it should be, yeah, so it should be that the derivative, the q derivative of x to the n is 1 plus q squared plus all the way up to the n minus 1 times x to the n minus 1.
So the opposite of that.
Well, it's the same thing. Yeah, because yours like n minus n is 0, n minus, right? Like,
Yeah,
yours
so-
works out to this. Just a simplification of it. And so we actually write this, we have a notation for this. Right like that. It's the Q number associated, did I get that right? I got it backwards. And in Q1. The Q analog of that. Why do we write it like that? Because we're dumb and lazy and don't want to come up with new notation for things. And I guess it should be in minus 1. Because, so the quantum derivative, the quantum analog of the Cauchy rule is this. In short. And try proving it if you haven't. And you can do it using induction. You've already proved your base case.
Yeah.
Either of you ever donated to Wikipedia?
No.
To give you those giant ads? No. I always see it and I feel bad because I use Wikipedia all the time.
I also never bought one as a kid.
Yeah, me neither. But like,
I didn't even pay
that was
for Windows
intentional.
key.
Really?
No, I was building a computer, my friend came over to build it with me, I bought us a pizza, and he brought the Windows key and did all the work.
Nice.
So,
Nice. guess I better scroll up just a little bit because it just gave you the answer to the product rule on that page.
Let's see, let's see.
Good. And another question on based on this e to the x is that so you know the normal derivative of e to the x is e to the x, right? It's the function whose derivative is itself. But it's not true in the quantum case.
Oh, what's my favorite thing?
Can you find a function whose quantum derivative is itself? You can do any of those problems you want. You don't have to like go in any order at all. I want to like turn off this front light that you see whatever.
I'm trying to cheat by looking at the Lagrange's shift operator, but I don't think that's gonna help me.
I don't think it's gonna help you.
No.
Yeah, the derivative with respect to ln of x. Want to try that?
Yeah.
That doesn't look fun to me.
No. I was just thinking, like, if you express it as an operator, you could find a fixed point to it. But that sounds like more work than just guessing and checking.
Yeah. It might be. That help you see that a bit better.
Yeah.
Cool. I don't mind if you read like what I have up there, because there's really not much there. But yeah, the quantum derivative goes to the normal derivative as it goes to 1. It's ugly. Or the Jackson derivative. There's also quantum integrals, right? It's the same thing. Just define it multiplicatively. I hate whoever messed up that table. It's like I always used to sit on that table. Now I can't sit there.
Swap the table.
I think someone did.
But the person who likes sitting on that table.
Probably. Right in front of the board though, like who wants to sit in front of the board? I guess tables are intended to be sat on exactly, but you know.
The room for teachers is it? For students.
That, exactly.
I think I've done the induction very wrong somewhere.
It's fine. Yep.
That's what I said.
Yep, that's right.
What was this get? You figured that was now.
Well, the rest of it you have, right? I think. Just double check. I didn't see it. Is that true?
Yes, it does. These are just sums of powers and
When you multiply that times that, like, I don't know if that factors, right? I think there's a,
because this has a q and an x in it, so I took that out, this had an x in it, so then I divided it by q. So that when I put it back in, the q takes it back. not cubing, sorry, she was understanding cube. That. So, yeah. Q and then Q here and then X and X is X. That's a good one. Q that crosses out the X.
But when you expand it back, shouldn't it be like 4 terms? Because you're doing binomial times a binomial.
Oh, right. No, I listened to yours. Right. No, this one.
I thought that was, I was looking at it, I'm like, something seems off here.
The minus sign is not right.
Yeah, something seemed wrong. I think, so it's a Q. I have an answer to this one that I did at some point. Let me look it up. F of X. Splitting, get that. Expand, you get that. Ah, I see the trick. I see the trick.
For the induction?
It's not induction.
Oh.
There's probably an inductive way to do it, but my proof does not use induction. My proof is this, so take this, DQ, maybe I'll write it over there, so I can, right over here. So, quantum derivative of x to the n is x to the n, well, q to the n, x to the n minus x to the n over qx minus x. Right? Then this is equal to x to the n times, I'm taking out a factor of x to the n from the top. And I'm left with, actually I'll take out, sorry, n minus 1. And I'm left with qx, is this what I want? Double check what I did. I factored out x to the n.
So everything else inside would just be normal, right? Or
Yeah. Sorry, factor out x to the n from here and x from here. And I'm left with q to the n minus 1 over q minus 1. Do you recognize that?
Should I?
Oh, that would be q to the n minus 1? No.
Oh. Check your formulas for summations.
That's something.
Yeah, I don't know.
It's one of those annoying ones.
I know like 3 of those, and it's like n squared and n cubed.
So this is actually the sum from q equals 1 to n minus 1 of q, well, I shouldn't write this as q, sum from I equals 1 to that q to the I. Which is exactly what you wanted. This is,
Oh yeah,
right?
that's just that thing.
Yeah. I think you usually see this as something that looks like usually you'll see it with R's.
Wouldn't you need the first number to be either 0?
Yep. You would. And I think it is.
Okay.
I think I just didn't write it properly.
I have an inductive proof for it.
Do you? Let me see.
Yeah.
Inductive proof.
It did rely on, I made an assumption that this would become this. I guess it's like a lemma.
Let's see.
That the previous steps, derivative times q to the x minus x would give you the next term, right?
What?
Going to my math, and if we have.
It would give you q to the n minus 1.
X to the n times the q to the n minus 1.
Yeah.
Which, when you put it in there, is exactly q to the n.
Yeah.
X to the n minus x to the n.
And that works because of the same thing over there.
Yeah.
Yeah, so if you have q to the n minus 1 over q minus 1, you're multiplying this by q to the x minus x. Q to the x minus x is just q times x minus 1. Sorry, backwards. X times q minus 1. This cancels with this.
Yeah.
Right? This term is 1 plus q squared plus q to the n minus 1. Minus 1. Or plus 1. Plus 1. Is that right? I just want to make sure my sign's right here. Minus 1. Either way, it works out. So yes, that should work inductively. There's probably equally. Is this mine?
Yeah.
What an equally inductive way to do this.
Actually, I have a couple questions related to some of the assignment questions
Yeah.
and some terms that I did not. Correct. Mine is with 4.2.8.
Yep.
It says in the answer hints whatever that f is not differentiable at 0. But then this says prove that this is differentiable from this interval, meaning that it is differentiable from 0 to infinity. But how can it be not differentiable at 0 if it is differentiable from 0?
It's okay. It's a weird quirk of the terminology. So, for it to be differentiable on 0 to what did you say?
Infinity and
Yeah. For it to be differentiable on that, like derivatives, you're thinking about a tangent, right? And you're thinking about like a secant off that tangent, and taking secants that are getting closer and closer and closer to the tangent. The reason why it doesn't matter that 0 is not differentiable is because there's nothing on this side of the, like on the negative side to take, right? So you could use 0 as like a limiting value, but you can't actually find the derivative at 0, right? Because there's nothing on the other side for that secant.
there's no way to and like the derivative means that the limit from the left and right are the same.
It
Or
means that the
that's
limit from the
differentiable.
left, well, you have a limit here, right?
Yeah.
So the limit has to be defined, which means that it has to exist, or it has to exist from positive and negative.
Okay.
Yeah.
And
So yeah, there's no negative limit, right? Because there's nothing less than 0.
And for this question here, 4.3, this is what I put for A. I'm very worried about being too simple. I'm just saying, it says they're increasing, meaning that the derivatives are greater than zero. And the way that derivative laws work is a derivative of f plus g is derivative of f plus derivative of g. If they both increase, and then they're positive, which means it's increasing. It's kind of like, it just seems.
So that's true. This always defines the true false. F and G are increasing, F plus G is increasing. Yep, you're right.
Alright, so I didn't underthink that, that's good.
Yeah.
For sure, he was right. The definitions that he gave for continuous and uniform continuous make no sense.
Okay, let me explain. So,
Oh, also before we get to that,
Yep.
I just want to confirm, the definition of derivative literally means that that derivative formula, the limit of h goes to zero, just exists.
yes,
Okay.
yeah, which means two-sided, right?
Yeah.
Yeah. So, the difference between continuous and uniform continuous
comes in the order of the quantifiers. That means gibberish to most people.
Yeah.
That's okay. So I'm going to try and come up with it. So, and I might get it backwards, so I might have to switch it, but it's like often get it backwards. So for continuous, it's for all. Do I have it in my notes? I might as well just pull it up in my notes if I have it, so that I don't have to. I probably do. Not recordings, I want notes. There it is. Cool. Okay, continuity. Let E be a non-empty set. So the first difference is that you're defining continuity at a point and uniform continuity on a set.
Yeah.
But you can define continuity on a point. Sorry, you can define normal continuity on a set. That just means that it's continuous at every point on that set. So for continuous, for normal continuity, so it says f is said to be continuous at a point A if and only if, given epsilon is greater than 0, there is a delta greater than 0, which depends on epsilon, f, and a, such that x minus a is less than delta and x is in E. So if you write it using the quantifiers, that's for all a in E, for all epsilon greater than 0, there exists a delta greater than 0, such that for all x in R, is it in R or is it in E? For all x in E, the equation holds that f of x minus a is less than delta implies f of x minus f of a is less than epsilon. So the key thing here is that if you read the order of these predicates, or these quantifiers, right, the for all there exists, you know, like you're adding information as you move across. So the first thing you know is what the a value is. You know the point that you're measuring at. Then you're given an epsilon. Then you can pick your delta, right? So you want to pick a delta based on that a. So as an example, if you're looking at like 1 over x, looks like this for the positive side. Here, you might just need a very small a, right? Like your a might be very small. Whereas here, you might need like a larger a. Yeah, you might need like a giant a.
Is a the point, or is a the? Because I thought it was a point.
Yeah, a is a point.
I
Yeah.
think I saw a graph saying like.
Here's a good visual for this. On Wikipedia, continuity. this image. So these are both uniform continuity. So the boxes there represent the A range, right? So that x, or I should say like f of x plus or minus f of a. And the reason it's plus or minus is because of the absolute values, right? Because we're thinking about the absolute difference between the two. It gives you like a range above and below. So the problem is, so with continuity, you can pick, with regular continuity, you can pick a bigger delta depending on the epsilon and the a that you're given, right? So you know that, oh, okay, this is like a really steep section, so I need to pick a really big delta, right? With uniform continuity, it's sort of the opposite. So it's like, with uniform, it's for all epsilon greater than 0, there exists a delta greater than 0, such that for all x and a in E, absolute value of x minus a is less than delta, implies that absolute value of f of x minus f of a is less than epsilon. So the a goes from the beginning to here. So if you read it out, all that you know when you have to pick that delta is epsilon. You don't know a. You don't know the point that you're looking at, right? So what you need to do for uniform continuity is to pick a delta value for it to be uniform continuous. You have to pick an a value that will work for every for any possible point that you're looking at, any possible spot along this curve, right? The a value determines where along the curve you're looking at. So you'll notice this red curve, it's always continuous here. It's always within the bounds. Like it might hit it's always hitting at some point the leftmost side of the box and the rightmost side of the box. And it looks similar for the blue, right? Like it looks like you're entering somewhere on the left and exiting somewhere on the right. But if you come back, there's a certain point over here where it's gonna start entering off the top and exiting off the bottom, right? So at that point, you haven't picked a delta wide enough. Like you need a wider delta for that box so that it would have worked, right? You need a different delta.
So, okay, so yeah, like at this point now, it's going up to the top, like it enters from the top, exits from the bottom.
Exactly.
And then now, as you go down, it starts entering from the right.
Exactly.
So you need it so that it always enters and exits from the same point.
You need it so that it always enters and exits from the right and left.
So you need, for blue, you need a smaller delta. Or you need a smaller, like the width needs to be, it needs to be a
Is that
thin
right?
box. Like a really thin box. Because when you get to the top,
Yes.
what determines the size of that box?
That's the question, right? So for normal continuity, you can vary the size of the box based on as you move along. You're allowed to vary, right? With uniform continuity, you have to pick the size of the box irrespective of where it is along that curve, right? So the question is, can you even pick a box narrow enough? Because if you kept going off to infinity here, like there's gonna be some point where even if you pick a tiny narrow box, it's still gonna do that. You're just sort of zooming in, right? So that's the thing with uniform continuity, is it needs to work always on your interval, right? Now if our interval we picked was, say, from here, for the blue curve, from here to here, it would be uniform continuous between here and here, because you could pick such a delta,
Yeah.
right? This specific delta would work.
But when you get to the top, there's no delta that can do that.
Exactly. There's no single delta that could do it for any value as you get closer and closer to 0.
In just words, what is uniform continuity? Is it just that it's continuous everywhere?
It's that it's continuous, not everywhere. It's that it's continuous on a certain interval for a concrete delta value. So a concrete width. And that width is uniform, like it's the same width. That's why we call it uniform, right? It's not really one of those ones you can quite easily put into words, but yeah, it's that you can pick a specific delta that works for every point, as opposed to just picking a delta dependent on the point that you're at.
So, if a function is uniformly continuous, it is continuous.
If a function is uniformly continuous,
And if a function is not continuous at a point, then obviously
it would not be uniformly continuous.
So I'm kind of getting at that uniformly continuous isn't as simple as just looking at a graph and seeing, oh, it doesn't disconnect.
Yeah. Exactly, because it looks like this function is continuous, right?
Yeah.
Like, if you look at f of x, if you look at f of x equals 1 over x on the interval 0 to infinity, the open interval, it's continuous on that interval, but it's not uniform continuous.
Because just by the theory of uniformly continuous, meaning that so anything that shoots up to like infinity or negative infinity.
Yeah. Yeah.
Alright, and then, well, no, because like, x squared, would that be uniformly continuous? It would shoot up to infinity, yeah, but it doesn't kind of have like an asymptote. which
Yeah,
is
so it
what-
doesn't shoot up fast enough.
Not depending on the interval.
It would depend on the interval. If you had like some closed or some bounded interval, then yes, it would be.
Like at the beginning, kind of.
Yeah, so like as long as your interval doesn't go off to infinity, right? Because even if we looked at 1 over x, say from 0 to 1, that's still not uniformly continuous, right? This is a bounded interval, right? There's
Yeah,
no
but
infinites here.
From 0 it shoots up to infinity.
From 0 it shoots up to infinity.
So
Whereas
I-
with x squared, if you looked at 0 to 1, it would be uniformly continuous between 0 and 1. But if you looked at like 0 to infinity, now it's not, right?
Right, so if it shoots up to infinity, then it's no longer uniformly continuous.
Yes.
And these delta and epsilon values,
Yeah.
do you decide, so you decide the epsilon first and then the delta?
So think of it like, whenever there's a for all, think of it like I'm giving you that value. And whenever there's a there exists, you have to pick it. So say that, so if we looked at this example with the red, right? Say I give you the function square root of x. And say that I tell you that we're looking at the a values between 0 and 6,
Yeah.
right? Well, actually, sorry, disregard that. Say that I give you the function, and I tell you that epsilon is 0.5. And I tell you I'll tell you the broad interval that I'm looking at between 0 and 6, right? Not a specific point, but just that whole interval. So then it says there exists a delta. So you pick a delta. Maybe I give you epsilon is 0.5, then you can pick delta is 0.2. And it works for the whole thing, right? So the for all, that's almost like you're given a value, and then the there exists is like you have to pick a value. Yeah. So that it works.
Do you have the quiz that we did last week?
Nope. I just gave it to Miranda. We'll get it tomorrow.
Okay, because there was a question on it that had to revolve around proving uniform continuity, and then
Was it uniform continuity?
either one of
It
them.
was, yeah, because I remember writing it's
Oh,
uniformly
yes.
continuous because f is continuous on the closed bounded interval.
Yeah, that was the thing.
I wrote
So,
that goddamn theorem.
and that's a theorem, right? So
Oh,
there's a theorem that says
Closed bounded continuous gives you uniform continuity always.
AB, this is a closed interval, bounded, sorry,
class in here. Closed bounded, and if you have a function which is continuous on AB, there's a theorem that says if those three things are true, then f of x is uniformly continuous AB.
Sorry, can we work in here?
No, there's a class in here.
Oh, there is?
Yep.
Okay.
Sorry.
Don't know how they see what's going on and think it's not a class. but-
Yeah, I don't know, but okay.
Yeah, okay, so I was supposed to go about proving it using the definition of uniform. Okay, that makes more sense, because what you were saying, like, well, how do I know what delta is?
Yeah.
Okay, so,
You usually pick delta based on epsilon.
You
anyway.
do, yeah.
In fact, I think always kind of.
Always you pick it based on epsilon, and if you're
Unless
doing,
for, like a constant function.
yeah,
But those are kind of trivial.
those are trivial.
oh, and in this graph over here, the epsilon is the height, and then the delta is the width.
Yeah,
Okay, so the epsilon and delta just make a box.
yes,
Okay.
exactly.
Do you have any other fun?
I haven't even started this on yet. That's like the Thursday problem, if not the Friday problem.
Nice.
I gotta.
Gave you
I
two
got-
back to back, eh? That's brutal.
I
I got like 3 or 4 assignments due Friday and a presentation that I think you were watching on Thursday.
Yep.
So,
That I forgot I was watching on Thursday.
hey, feel free to not show up and then give us all 100%.
Oh,
I won't-
that'd be great.
I won't complain about that.
Oh, neither would I, but.
Where am I?
and then Riemann
Integrability.
Yeah, I don't quite understand that, and the definition of a partition is way too many I's and J's.
Too many I's and J's,
Yeah,
eh?
Is it just a look at that definition? Can you remember?
Back to Calc 1, when we were doing like the midpoint rule and the left hand point rule.
I remember hating that. I remember like
That's
basically-
a Riemann integral.
like the whole like
Not
box
quite,
here.
I don't think, but that's a Riemann sum. Like for him.
Yeah, that is a Riemann
And
sum.
that makes sense why I remember that name. I don't know where I remember it from. So, from all I got is that you basically break up, well, it's like game inputs, you break it up into a bunch of x inputs and find the function.
Yeah, the partition is just like this set of all of the endpoints of your rectangles.
A bounded function on a compact interval. Yeah, you don't know compactness, so that's not a helpful definition for you.
What is compactness?
Compactness is a property that seeks to generalize the notion of closed and bounded subset of Euclidean space. The idea is
For us, it's just closed and bounded.
a generalized of it. Let's see. Let's go to definitions. Subset of Euclidean space is called compact if it's closed and bounded. This implies by the BW theorem that any infinite subsequence that converges to a point, or sorry, has a subsequence that converges to the point. That's sort of the way that I think about a compact set, is that BW holds Bolzano-Weierstrass, which to you means that it's closed and bounded, but that's not always true. That's just true in real numbers. And some other spaces, Euclidean spaces. But either way, let's see what he put for thing. Real analysis. I know. I don't know. That's a him question. He does that for every course. This is not just, I think just because he has it stored probably on Dropbox, and it's just easier for him to just share the Dropbox with you. Yep. Yeah, you can't download unless you.
Yeah, no, I've never downloaded the lecture notes.
So let's see.
If
integrability, yada yada. Partition of, well, let's go through the partition of an interval. Yeah, there's like 3 screens. That one's not on, but.
Very impressed that you knew what it was saying probably.
So the partition of an interval is a set of points such that A is equal to the left point, series of points. Yeah, so a partition is just like, I can explain this in very layman's terms. It's a way of chopping up an interval. So maybe you go like boom, 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 boom. They don't have to be evenly spaced. They don't have to be anything. They can just be chopped up in any arbitrary way. Here, you label, if this was the partition, you label this x0, x1, x2, x3, x4. So the partition is those, I guess, 5 points between A and B. Well, including A and B. So probably should review this with the definition of B. X naught, 1, 2, 3, 4, 5, 6, including the 2 points. So you're just chopping it into sections. Yeah. So let's see, the norm of the partition, I don't remember half of this, so the norm of the partition is the number, the maximum of the difference between any 2 consecutive j's. The max between, so it's the max length. It's like, check the lengths of each of these. Right? Whichever one's the biggest, maybe this one's the biggest. That's your part, but that's your norm. Refinement of a partition is a partition of A, B that satisfies, so it's a subset of it. In this case, we say that Q is finer than P. Yeah, so, so you have A, B. Let's say that your partition is just 1, like you just split it in half. It's your partition. So in this case, the partition would be, well, let's take some specific examples. Let's say that this is -1, 1, and you pick 0 as your sort of extra partition. So you get -1, 0, and 1 is your partition. Right? What's the norm of that?
Would be
Yeah. It's like the max distance between, max gap, if you want to think about that as well. Just works out that these 2 are even, it doesn't have to be.
refinement.
So a refinement would be something like this. So we say, okay, well, what if we add another point? Maybe let's do 1/2. So now Q is -1, 0, 1/2, 1. What's the norm of Q? Oh. It's the biggest gap, so it's still 1.
Oh, biggest, sorry, my mind is.
Sorry, yeah, it's the biggest gap. So the refinement, all it means is that, like, let's say that I'm giving you a bunch of random numbers between -1 and 1. Right, just spitting out random numbers. With key, you sort of have 2 boxes you could fit them. You could fit them in between -1 and 0, or you could fit them in between 0 and 1.
Yeah.
Right. With Q, it's like finer, like you have more granular control. So you can fit them between -1 and 0, or you can fit them between 0 and 1, or you can fit them between, sorry, 1/2, or you can fit them between 1/2 and 1, right?
Yeah.
So it's like more detailed, right?
Refinement.
More fun. Yeah. refinement, right? It's like finer.
And so we just say refinement is like kind of like a sub.
Yes.
Is that just
The opposite,
same
though.
AB and you just make more points?
Exactly. So it's the opposite. So you'll notice he wrote it as
You make a subset.
P is a subset of Q, not Q is a subset of Q. Because Q gets extra points
Oh, yeah.
to make it fine, right? So Q's getting bigger. So it's the other way that you would think.
Alright, and if Q is refinement, then, okay, yeah, because you can't have. Okay.
Mhm.
And then, so for Riemann, now that I've kind of understood what that meant, so a Riemann's
Integrability.
Yeah, that is basically the limit as the max distance approaches 0
Yes.
for, and this is RFP. Does that function from R and then the subset?
So
Oh, there's one.
So the first thing is that you want to know what the upper Riemann sum and lower Riemann sum are. So the difference there is one of them, you're taking a partition, you're dividing the interval into a bunch of chunks. Then you look at the function over that interval. For the upper Riemann sum, you're taking the minimum of each point along the interval. So as an example, if you have like, if this is your partition, you have your function that looks maybe like this, right? The minimum, so for the lower Riemann sum, the minimum along this here would be here, the minimum across here maybe is like here, and the min across here is like here.
That's the lower.
That would be the lower. For the upper, it's the opposite. So it's the peaks, the max of each. And again, the partitions don't have to be even, right? So then the Riemann sum is just the sum where that choice of the point that you evaluated at is arbitrary. So you pick an arbitrary point. Could be the max, could be the min, could be something in between. And then, so we said, let AB be a real number with A less than B. A function is said to be Riemann integrable on AB if it's bounded. This is 10.014 on notes 12.
Okay, I remember seeing the definition, and then the next definition I found for it was completely different. And then I just thought I misread it, reading that. Okay,
Sure.
I didn't see this one. I'm looking.
So let AB be real numbers with A less than B, so you have some interval. Function goes from that interval to R. It's said to be Riemann integrable if the interval, if f is bounded on that interval, and if for every epsilon greater than 0, there's a partition such that the difference between the upper Riemann sum and the lower Riemann sum is less than that epsilon, for every epsilon. So you take the sum that's like this of how do we draw this? Here. The sum that would look like this. Right, that's the upper sum.
Yeah.
The lower sum would be like this. Okay. And so the difference between the upper sum and the lower sum, you want to make sure that it's less than some epsilon for every epsilon there. You can find some partition, find some way to chop it up so that the difference between the lower Riemann sum and the upper Riemann sum is less than that error.
So kind of less than that.
So in other words,
it has to be positive. No.
well, it's always going to be positive, right? Or 0.
Yeah.
The difference, because u is always going to be greater than or equal to the L. But maybe another way to phrase it is that, like, as you get finer and finer partitions, right, and you keep adding more and more ticks basically along that interval, the point that you choose doesn't matter, right? Because like the difference between the upper and the lower bounds is getting closer and closer and closer, shrinking and shrinking, right? Here we have pretty big gaps.
Yeah.
But if we made this integral or this interval smaller and cut it up, those gaps would end up being smaller,
Yeah.
right? They get more and more precise. That would mean that it's Riemann integrable.
So basically, upper minus lower is
Less than epsilon.
less than epsilon, which is greater than 0. So can upper minus lower be a negative number?
No, it will never be negative.
So basically, it's 0.
It could be 0, or it could approach 0, right?
Okay, so approaching 0 or. Sorry, when I see the E greater than 0, I keep thinking of the case, or epsilon greater than 0, I keep thinking of the case that epsilon is like 0.00000.
Yeah.
But then there's cases where it could be like 5.
It could. It could be 5. It could be anything. But usually you're concerned with the cases when it's smaller, right? And then here's a theorem, which is that if f is continuous on the interval, then it's integrable on the interval. So continuity and integrability are the same thing. Yeah.
And then the last slide had a different. This is a theorem.
Upper integral and lower integral?
No, the last one.
Oh, I see. Keep going.
This one.
This one, okay. Let a, b be real numbers with a less than b, and suppose that f from a, b to r is bounded. Okay, then f is Riemann integrable on a, b if and only if the limit as the partition shrink of the Riemann sum is equal to the limit as the partition shrink of the sum of choosing any arbitrary point exists, in which case, yeah, it's a really ugly way to say it, but yes. In which case the integral is equal to that limit. So basically this is just saying that the integral, which I don't think they actually defined, like they sort of defined them separately. So they just, this theorem just relates the Riemann sum, the limit of the Riemann sum to the integral. So if the limit to the Riemann sum exists, then it's Riemann integrable, and the integral is the limit of that Riemann sum as the partition shrink.
What about these, the second definition, or can I rely on these?
Well, it's not really a definition, right? This is just,
I'm just saying that the limit of the
yeah, the limit of the Riemann sum is the integral. So that defines what an integral is, as opposed to this, which defined what it means for a function to be Riemann integrable. It just connects the two ideas together, Riemann sums and integrability. Don't cancel this.
So upper minus lower of the upper Riemann minus lower Riemann will always be greater than 0.
Upper minus lower will always be greater than 0. Yeah.
Can you give an example of a case where it's not Riemann integrable? Is every function that's integrable Riemann integrable?
Yeah, because when we say integrable, we mean Riemann integrable. We're just being lazy and dropping the word Riemann.
Okay, so basically any question that says, is this Riemann integrable, it's basically
they're the same thing.
So there's no function that is integratable and not being integrated.
Yes, there is. Well, sorry, no, there's not.
Okay.
But there are functions that are not integrable.
Right.
What about the Dirichlet function?
Piecewise things are cheating.
No, it's not.
It's to be. Always make the case. Right. So 0 if
X is rational. 1 if X is irrational. Does someone have a class in here after?
They had one last week.
I don't know.
I feel like
Oh,
last
someone
week
had a
there was
meeting or
something
something.
last week, but
There was a meeting.
usually there isn't.
Yeah. If someone has a meeting, they'll just come in.
why is
Give
that
us-
not integrable? It's just
Why is that not integrable?
you can integrate 0. 0 would be
Yeah, but the function looks like
oh, right.
this, right? It's like some weird function that doesn't actually, like, it's not continuous,
Yeah.
right?
So,
It's continuous nowhere.
okay, so non-continuous functions are not.
Yes. And I think that was the theorem in if and only if? No, it was just one way. If it's continuous, then it's integrable.
Alright, so if it's continuous, it's integrable, or integrable, it's Riemann integrable.
Yes.
If it either proves something is Riemann integrable, can I prove that it is general integrable? Because I started doing that with proving things are Cauchy,
Well-
so if thing is real, I just started proving it was
Whenever we say integrable, that's just like us being lazy. Like, it's the same thing as Riemann integrable. Like, they're identical terms. There's no difference. So, yeah, like anytime you see integrable, you can replace it with Riemann integrable. And anytime you see Riemann integrable, you can replace it with integrable. They're identical.
can I do that? I can do that with Cauchy and convert it to.
Yep.
convert it back.
Well, yeah, you can.
Yeah, as long as I state that it's integral, so the real analysis I can just.
Yes. If you go on to complex analysis, you cannot do that.
Yeah, I'm not gonna do that. I realize I have to do analysis on my head, make sure I doesn't convert.
It's not as bad as this, I think.
Yeah.
I think it's the end of it gets a little weird. Well, I can show you. I'm sure I have my notes. The end of it does get a little bit weird, but I think I guess I should end the recording. I don't know if I actually did. I'm just talking. Yeah, I did not end the recording.